Yeah, all right.
Great. Cool. Thank you very much. So I actually don't own the university, so you're more than welcome to walk around the facilities and I won't say yes or no. Yeah, so I'm Paul Smith. I'm a prof here in the School of Computing and Communications, and I do research on critical infrastructure security and resilience with a bit of a focus on energy systems, so energy distributed systems and that sort of thing. And what I'm going to try and talk about today is sort of some of the risks and benefits associated with using various sorts of digital technologies, computing technologies in this context. So I have another version of this talk, or another slide is like basically helping kind of maintain, keep the lights on whilst we're sort of using these sort of technologies like AI, ML, and digital twins and all this kind of stuff. So I think there's a sort of tendency in the security community to sort of think about these technologies, in particular in the critical infrastructure sector, think about technology innovation is a necessarily negative thing, right? It introduces sort of more vulnerabilities and stuff like that, which is true. But there's also sort of opportunities with the use of these technologies to support cybersecurity. And I'm going to try and talk about a couple of, I think, use cases that we're working on with some smart people, mainly students in this space. All right. Does that make sense? Making sense? Yes. Good. If you want to interrupt me and tell me I'm speaking nonsense or too fast, go for it. Yeah. I won't be upset too much. Good. All right. So as we all know, so the infrastructures are by these sorts. And now I'm going to move a lot. Guy, please walk forward. So critical infrastructures are providing all sorts of important services that make sure society functions. Right? We all know this. This is part of the stuff. Electrical energy and distribution system, water supply. So there's a talk on transportation, railway, in this session, which is really interesting. These are sort of being increasingly digitalized. So basically using computer-based systems or computing systems. So in the past, a lot of these infrastructures operate with entirely analog systems, right? So non-computerized. But for various reasons, to sort of start to use more and more sort of computing technology. And sort of a part of that kind of digitalization is a sort of convergence of what we think about as information technology, sort of things that we sort of use on a day-to-day basis, some commercial off-the-shelf equipment, laptops, Microsoft operating system stuff with sort of operational technology, which is typically quite different in flavor. I'm going to talk a little bit more about what form that IT and OT sort of convergence looks like. Already done already on this Teams. So there are many benefits associated with this digitalization, but there are also risks. Okay? Benefits, but also risks that we need to think about. All right, so this, who's heard of this term IT/OT convergence before? Roughly speaking. So basically, the kind of traditionally sort of operational technology was sort of very practice-state operating in a sort of different sphere, with the sort of purview of engineers, control engineers, and that sort of thing. And sort of organizations wanting to sort of optimize the performance, the operations and stuff like that, try to kind of increasingly connect and integrate the business side of the organization with the operations. Yeah. So we get data out of those systems. And to be able to do things like predictive maintenance, for example, so like if a turbine, all the time wears, if you can kind of predict when it's going to fail before it catastrophically fails, you can save yourself a lot of money. So that's kind of why we're trying to do this. And sort of this, kind of my attempt to be sort of P-side-ish, is that, this is sort of seems a bit of a holy mark of critical infrastructure security's kind of integration. And there's two ways to think about this convergence. One is from an architectural point of view. When I say architecture, I kind of largely mean network systems architecture. Yeah. So in the past, OT systems, the stuff that sort of you can find in electricity substations, nuclear facilities, water delivery systems, and this kind of thing, is disconnected and separated by a so-called air gap. Who's heard of an air gap before? Right. So there's this sort of funny thing, like unicorns and air gaps, what they have in common, universes. Right. There's a sort of funny joke in this sort of field. It's still a very useful way of securing these systems, right? So basically, the idea is they're not connected to sort of these critical systems are not connected to other ones. So if you want to do updates, you've got to use things like removable media, USB pen drives, and so on. But this is changing in several ways. So enterprise systems, so the kind of things that you see in the business side, being connected to them via a DMZ, military software, to get basically data out of sort of specialized databases called data historians. And the idea is you can run models all over the top of that to see when things are going to fail, when you need to replace widgets, and all this sort of stuff. This is a sort of long-running thing. Vendors and suppliers of the equipment that go into OT environments would like to have remote access, so that they can do maintenance. So from the internet, so we sort of VPN deep into the sort of critical infrastructure that you operate, which obviously reduces risks. So there's a lot of talk about supply chain security. So what are your suppliers doing, ensuring that your suppliers are secure as they sort of access your critical assets. Increasingly, field devices of different sorts, so the things that you find out in the field that are sort of operating substations and so on, want to try to connect out to services. So anecdotally, in my old place, we were working on a digital substation, and we plugged in this device, and it wouldn't work until it could connect to a cloud. Right? So this is a sort of a trend that's going on. And then the kind of devices that you're using to maintain and configure them are sort of internet connected or commercial off the shelf. So if you think about this term Industry 4.0, so there's a lot of new technology in this space, tablets where you can monitor the process, control set points, how you configure it, and so on. So anyway, what we end up with is lots and lots of ways in and out of the system that were typically previously not connected to each other, which makes our attack surface a lot larger and introduces a greater risk. The other kind of side of this is that there are sort of technology changes that sort of were typically thought of as being predominantly from the IT domain, moving into the operational technology. So these were historically very limited pieces of technology. So the canonical sort of bit of technology that you would use is a programmable logic control. So this thing sort of gets measurements from the real world, runs a control algorithm, and actuates to change things like open the breaker, change a valve, make a turbine spin faster, whatever. So these are sort of industrialized pieces of equipment that should roll on, in retrospect, just to show you. But they're sort of very, very kind of limited in their capability. So they're running like a real-time operating system, and that's about it, right? Not a lot else. And the other thing, historically, they were very, very poor from a security point, right? Because that was not really a thing. 10, 15 years ago, you sit in the field for 20, 30 years, so people like you who like to hack things can have a lot of fun with them. This is changing. So they're getting increased computational compute capabilities, so they have more compute, more memory, more storage than they ever did before. And I'll give you an example of a type of device that's in that direction at the moment, using virtualization platforms. So basically being able to use virtualization to run like the real-time operating system part of the system, and then other kind of more general purpose operating system part of embedded Linux, so you can run services on them. If you were into sort of, I think there was a competition for, if you say certain buzzwords, you have a drink, right? Digital twins is another good one. Yeah. So digital twins, there's a lot of talk about using digital twins in this space. So basically, these are sort of virtual representations of the real world system that you can do analytics on. Again, things like predictive maintenance. So it's like a model that collects data from the real world, feed it to your model, and then use that to support decisions about how to operate, sometimes autonomously, sometimes with computing in the loop. And these sort of, there's a kind of an implied, often when you talk about digital twins, implied use of the cloud to sort of locate the models. Of course, our friend AI and ML, which we heard a lot about before the break, and internet protocols for monitoring and control, or internet-like protocols. So historically, these protocols that were used to control industrial control systems were often closed, so not open like you would get from the internet, and a little bit obscure, right? So there's a bit of security by obscurity going on. But sort of some examples of kind of industrial control systems are starting to use more internet-like protocols. So before coming here, I was involved in a project that was looking at electric vehicle charging infrastructures. So the sort of things that you put your car on the side of the road. They're controlled using a protocol called OCPP, Open Charge Point Protocol. And that's entirely WebSockets JSON based, right? And the reason to do that is because it's cheap and easy to develop implementations of that compared to what it was in the past. Right? So you get to market quicker. So there's that kind of drive to use more of these kind of internet-like protocols. And then scary things like app stores. So these programmable controllers that have apps running on them. Which is really cool and interesting, but these are sort of apps running in the core of your critical infrastructure. And, what happens when it goes wrong? You go to Schneider Electric or Siemens, Phoenix Contact, or whatever, choose your favorite vendor. And what, anecdotally, we found is what they'll say is, well, that's not our problem. You need to go to the app developer. So again, this is sort of an interesting issue around how to handle that. Response. So I've sort of tried to lay out some of the risks. So they're kind of basically where the sort of industry is going, I suppose, in terms of this digitalization. How are we feeling about that? Confused? Concerned? Yeah, you should be. Which is why you need to fund research, whoever.
Also, good plug.
You have to get it in there, right? All right, so what I'm going to do is talk about some of the kind of risks and benefits of this digitalization that I've been working on with some PhD students and stuff over the last years. So the first thing I'm going to talk about is our friend machine learning. Everybody's an expert on machine learning, right, in the room? Yeah. You're an expert? Ace. Yeah, an expert is always a relative term, right? Relative to the other individuals in the room, right? So basically, the way kind of machine learning works is basically you have a training phase, we have a bunch of training data, you do some feature extraction normally, so if you're using network data, for example, network traffic like raw packet captures or something like this, you could do some feature extractions or looking at the entropy of ports and IP addresses and how much packet lengths and all blah, blah, blah. And then you train, test and validate some model, right? This is for predictive machine learning, not the kind of Gen AI stuff that we were hearing about before the break. Right? It's a little bit different, I think, in that context. I'm not really a Gen AI person yet. And then, no problem. And then the sort of, then once you've sort of trained your model, you sort of then use it operationally. So you get some sort of sample, an image, a network flow, a summary or something like this. You query your model and it hopefully gives you an inference of prediction. So is the image a person or an animal or a certain type of animal? Is the flow representative of the denial of service attack or a port scan, or is it benign or malicious, depending on what kind of model you're using and what it's being used for? And all through this kind of like, if you like, life cycle and from training phase to operational, there are different types of attacks that could manifest. So you could poison the training data, steal the model, query the model to find out about the training data. All sorts of different sorts of things that you can do. And lots of research is going into sort of how you kind of, what are the different types of attacks and how do you protect machine learning models to store. I worked with some colleagues a few years ago on a particular type of attack to machine learning models called adversarial examples. Aside from the 439 students, who's heard of adversarial examples before? Good. So we have some experts in the room. Basically what they are carefully crafted inputs to a machine learning model that are intentionally crafted to subvert the prediction that the model is making. Yeah? So you make manipulations to the query. In this little example here, this is a sort of very classic example by Goodfellow, where you make modifications to the pixels of an image so that we can't see any change, but the machine learns by basically adding a bit of noise, or some noise, and then the model mispredicts. Yeah? So the machine learning model thinks it's given. So you take a trained model, manipulate the query, it gives you an incorrect classification. And there are different classes of this type of attack. So targeted attacks where you say, I want this input to be always benign, or I want always to be a port scan, or always to be given whatever it is that you want to do. Now this sounds like a lot of fun, right? Yeah? It's really, really cool. Until you start using machine learning models in critical infrastructures that are supporting control, for example. So there's a lot about sort of model-driven control, manipulating the sort of control behavior of systems, like what are the set points and all this kind of stuff. And if you use machine learning for cybersecurity, right? So there's a lot, I'm sure you've heard, of kind of work looking at products that ought to use ML to support things like virus detection and network traffic classification. Yeah? Yeah? So, exactly, yeah, Darktrace, for example, is a good example. So, one of the things that some colleagues and I looked at is to see if we could generate adversarial examples for inputs to a model that's being used to do network intrusion detection. So in this case, we were looking at sort of multi-class classification models doing multi-class classification. So basically, you feed it a network flow, a network summary of a network exchange, and then the model predicts what it thinks it is. Is it benign? Is it now a service attack? Is it a port scan or something else? Yeah? What's interesting about this, or challenging about this, is that unlike a sort of Panda, where the constraint is only that it needs to look like a Panda to you and I at the other end, you can't arbitrarily change the features of a network flow. There are constraints on how you can manipulate the flow, because it very quickly doesn't make any sense. So if you change one feature, it has to be consistent with the other. And if you're an adversary out on the internet, and you want to essentially generate flow records by changing your behavior a little bit, there's only certain features that you can affect. Because, for example, you don't control features related to the reverse direction. That making some sense? Yeah? Good. Finally, this was 2020, so it's 2024, yeah. Thank you. I've been able to explain this in a useful way. Anyway, so the long story short is that we were able to generate adversarial examples by manipulating. So basically what we did is we had an algorithm that was manipulating features and giving it constraints. We said, you can't touch these features, go wild on these other features, yeah, because these are things that we can control arbitrarily. And generate an adversarial example to cause misclassification of a network flow. And what we were able to do was sort of get similar, I'm not going into the details of this, get similar sorts of results in terms of our ability to craft adversarial examples and respecting the constraints that are in place with respect to network flows. Does that make sense? Yeah. So these problems exist all over the places like physical systems or industry control systems, right? So if we have machine learning models that are supporting the behaviour of the control system that's in the electricity distribution line, you can't arbitrarily change things like phase, voltage, power. There's this laws of physics in place, right? So there's kind of interesting sort of parallels in the type of physical systems domain where these models are being used, and some people have done some work on generating adversarial examples for those sorts of systems. So that's a big risk, and there are lots of kind of ways that you can make these sort of models more robust to these types of attacks. So you train them in an adversarial way, but it's never going to be perfect. So the attackers are going to get smarter or whatever, or will miss it or whatever. So we now need to account for that. Right, I need to pick up the pace. Just to give you a bit of a flavour of some technology that we've been playing with. So as I mentioned earlier, there's this kind of ITification of industrial devices. So the sort of industrial device sits at almost every critical infrastructure that does some sort of process control. There's this thing called a programmable logic controller. It's a sort of industrialized device that's meant to sort of sit in hostile environments. And it normally runs, like I said earlier, on a real-time operating system. And you basically provide with a sort of user program, which is a control program, take some measurements, make some sort of decision, and then actuate to something like a PID control with the control systems engineer. So Siemens have this product, the S7-1518 MFP, multifunction platform PLC. It's all about Industry 4.0, sort of improving efficiency and all this kind of stuff. And they have this functionality on there called a C++ runtime, and it's basically a sort of modified version of Linux that you can stick on this little PC, this little PLC that sits, for example, on your car manufacturing plant, and you can kind of run the program on here and get information about the process via a protocol. And there's a virtualization platform. Sounds like a horrendous nightmare, right, from a cybersecurity point of view, right? If you introduce this sort of general purpose operating system into this environment. So we saw this and we saw an opportunity for cyber, right? So what we did is we came up with this little tool called Goosewolf. I left my student alone for a little too long and he came up with his name. Because goose makes noise and the wolf is a predictor. I don't know. I've got shoes, it's gross. And basically what we do is monitor the state of the PLC, so like, has it been restarted, are the cycle times changing, and also monitor whether it's controlling the system correctly. Is it trying to apply unsafe control actions? Okay, if it is, it generates an alarm. And this is a sort of way of implementing some good practices for PLC security coding. So there's an opportunity for this, right? And we can put it right on the PLC, so we have a smaller attack surface. It's harder potentially for an adversary to manipulate it. Digital twins, this is a thing that's coming. People are investing vast amounts of money in digital twins, largely for operational reasons, do things like predictive maintenance and so on, as I said earlier. There's a lot of security issues around the use of digital twins. So the twin itself represents a lot of intellectual property, and if you're in certain sectors, it represents sensitive information about the operation of the facility. And you also have a control loop, right? You have measurements coming out, controls going in, right? So you can manipulate this, and manipulate this, manipulate this, and you can make bad decisions, right? If this lot doesn't represent reality, things can go wrong. So you need to protect it, like with any other control system, right? What we've been looking at is, can we use a digital twin to support cybersecurity incident response for critical infrastructures, where usually there's a bit of a disconnect between sort of IT incident response, we have like an IT security operations center, and maybe there's an OT and operational technology security operations center. So we can use the digital twin to get situational awareness, use it to do all sorts of different types of queries about, okay, if I change the system, what's the behavior that's going to occur because we have like high availability requirements. So making changes, different pressure is difficult. All right. So this is my research peacock. I said peacock. Sorry. You have to be of a certain vintage to appreciate where that job comes from. So there's all this digital technology coming, right? And we could just sort of bury our head in the sand and say it's a terrible idea, stop doing it, and then life will carry on, and commercial enterprises will keep having these capabilities, these systems, and they'll find their way in. We can't do that. We've got to somehow embrace, to some extent, in a risk-informed way, this sort of innovation, these technologies. And some of this innovation, some of these things are necessary in order to operate some of these critical infrastructures in a way that we need them to do in the future, right, to be cost-effective. Like, if you think about renewable energy systems, or energy systems with renewable energy sources, we need to operate them in a smarter way than we do now, right? So, what we need is sort of approaches to realize the use of these technologies in a safe, because safety is a huge topic here, and secure way, right? So we need sort of technologies that are robust to attack, right? So all of the stuff that we do around hardening systems and all that kind of stuff. And when we think about AI and ML, we need to train our models adversarially, right? And keep training them, do pen testing against our AI, all that kind of stuff. So the core of the technology is as secure as we can get. Then we need to think about how these technologies assist in a wider system architecture, right? Applying principles, things, like defense in depth, which is sort of well established in this field. Having guardrails in place. So if the AI model tells you to do something stupid, there's like a limitation layer that says, no, don't do that. That's not safe. So stop doing it. People and organizations. A lot of the use of this technology implies modifications to the way that we operate critical infrastructure at the moment. Or more digital, more convergence. So there's human performance issues that we need to come up with, there's process issues that we need to address. Regulation, of course. So we can all come up with some really, really great ideas, all this innovation, and then the regulator says, sorry, it's not safe, too hot. And then we spent billions or millions on the technology for a particular context that's not meeting some sort of regulatory approval. So we need to think about how do we give the tools to regulators to support analysis of these technologies in place. And how do we make a case as people that want to use these potentially to a regulator that the use of these technologies is safe and secure? What are the tool sets? What are the arguments? So the nuclear we talk about arguments, evidence, cases, arguments, and evidence. So how do we develop that for these types of technologies in respect? And of course, we need good guidance and standards, right? Good practices that we can follow. Some of those are coming, right, for the use of AI and ML, but that's probably still a little bit early. There's a summary. I guess my kind of takeaway is when you look at this there's a bit of a tendency for us to sort of think about these things in a very negative fashion, right? So let me see if we can flip it around and say, okay, what opportunities does this realise for cybersecurity? And then how do we go about introducing some of these technologies in a safe and secure way? I want to say thanks to all these very, very clever people who helped me, or actually did all the work. I'm just the mouthpiece. Thank you.